Here is the DSB Mark I. This aircraft was designed with flight performance, ease of assembly, and functionality in mind. The pandemic that has been going on globally over the last year has affected everyone, with increases in cases in rural locations with no easy access for medical supplies and alternate approach was required. Our mission was to fulfill the goal of supplying medicine to a remote island. This is important in this time when vaccines are required to be moved quickly between refrigerators, and this would be impossible via other means. Our plane is a standard configuration with dimensions of 600mm in length, with a width and height of 100mm, giving space for the payload and internal electrical components. The wingspan is 1192mm, with an aspect ratio of 5.25, and an airfoil chosen was a Falcon 56 Mark II. The tail volume coefficient was calculated to be 0.39 with a tail setting angle of -2.1 degrees. The max takeoff weight of our plane is 0.91 kilos with an operational empty weight of 0.78 kilos. With a cruise speed of 18.8 meters per second at an altitude of 200 meters, a maximum range of 39.5 kilometers at MTOW, the Mark I can reach remote islands with ease and speed. At the MTOW, the maximum endurance of the Mark I is 72 minutes, giving the capability to hold if it is not safe to land for any reason. The propulsion system chosen utilizes a brushless DC electric motor. The motor chosen was the T-Motor AT2308 with an 8060 APC propeller. This combination of motor and propeller was matched so their efficiencies were best for our chosen cruise velocity. Due to the range of the mission, a flight controller was needed for automated flight, and the Pixhawk was the perfect candidate. The Pixhawk system utilizes an array of sensors to determine the attitude and position of the aircraft, as well as flying it to its other side location. For the initial ascent and final descent, a pilot in command can use a short-range RC transmitter to take off and land the plane. The mission requirements were to deliver medical supplies to remote islands 10 miles away in headwinds up to 10 miles per hour and gusts of 12 miles per hour. Medical supplies can often be required quickly. This meant that our design would need to be assembled by a remote engineer in short time. This requirement was the most constraining as it forced us to trade off design performance to keep manufacture and assembly of the components within the specified time. We also developed some key performance indicators to verify our prototype behaved as intended. Examples of this are ensuring the launch angle was between 0 and 45 degrees, logging flight data for post-flight analysis, and that deflecting the elevator gave the desired pitch rate. These were all checked with flight tests and verified by recording the flights to video. Another key consideration was safety. We created protocols in the case of an emergency, such as passers-by going into a dangerous area, we would cut down the plane safely. The cut-down procedure can either be initiated by the pilot, or during long-range sections, it can be done automatically. Our design process involved creating bespoke design tools that aided our initial design. This enabled us to make rapid prototypes and run simulations to ensure its success. For example, we used experimental wind tunnel data for the airfoil and propeller so that we could estimate their performance. We also thoroughly tested the materials that we were provided. These tests informed our final decisions on which materials to use for which parts of the aircraft, and this was based on both bending and torsional tests. It also helped us give an initial estimation for the structural mass of the aircraft for weight estimation. To test whether our plane would fly in an acceptable manner, we utilised Simulink's flight dynamics modelling simulation tool, as well as writing our own C++ code for verification purposes. This gave us the confidence that our design would work well in different flight states. When creating our CAD model, we linked our CAD design with Excel, so the changes could rapidly be prototyped and that we could explore the effect those changes had. By use of Python simulations, we are able to rapidly test a myriad of configurations and parameters such as aspect ratio and static margin. This gave us the optimized solution for each parameter to ensure that we got the best performance possible. We created testing criteria to ensure that our aircraft was able to carry out the maneuvers necessary to complete the mission. Each criterion had specific conditions for passing or failing the test and is visible in the OSC4 document. The tests were undertaken at different CG locations to verify the static stability of our aircraft. The first test was the launch procedure and maiden flight. The measure of success was the aircraft did not stall immediately after launch and that the log data was consistent with the flight recording. We then tested the longitudinal stability by verifying the CG coincided with the aft limit, and then the elevator produced pitch while in flight. The final key test was to explore the lateral stability of the aircraft. Similarly to the previous test, the CG was verified and then the control surfaces were actuated to see if they produced the desired effect. Our test came out inconclusive, and due to the variety of factors, it made it difficult to verify our key performance indicators. This was partly due to adding ballast to the plane so we could reach the correct flight weight in spite of having no propulsion. Without the propulsion, the aircraft was unable to meet its true performance capabilities. When the aircraft is hand launched, the aerodynamic drag quickly brings the aircraft to a state of stall. Despite this setback, the DSB Mark I is still capable of unpowered flight and provided us key data through the onboard data logging for future improvements. From building the Mark I, the aspect that contributed the most to build time was skinning the wing. The material used was not ideal for the mission as the stiffness caused cracking in the skin. For the DBS Mark II, The manufacturing technique will be altered so it is easier to do and thus reduce the overall build time.